In this part of the lecture, we explore an application of GRNNs, epidemic modeling, and compare them with GNNs and RNNs. The epidemic modeling problem consists of modeling the spread of an infectious disease over a network of friends as a graph process, and using samples from this graph process to predict the number of infected people at a certain point in time. The underlying graph is a friendship network built from real data from a high school in France. To model the spread of the disease, we use the susceptible infected removed, or SIR model. At any point in time, each individual in the network is either susceptible to the disease, infected by it, or removed once they have contracted the disease and recovered. We will compare the ability of three architectures, a GRNN, an RNN, and a GNN, to predict who will be infected in 8 days. To build the friendship network, we use real data corresponding to friendships reported by a group of 134 students from a high school in Marseille. Each node of the graph represents a student, and each edge represents a friendship. All edges are unweighted and symmetric. Isolated nodes were removed to make the graph fully connected. In order to model the propagation of the disease, we will assume that friends spend time with each other, and thus the disease is likely to spread from friend to friend. To model the spread of the disease, we use the SIR model. At time 0, we randomize who has the disease. Each student may have it with probability 5%. That is, roughly 1 in 20 students will have the disease at day 0. At any point in time, each person is either susceptible, infected, or removed. Their states are updated every day, and the transitions between states are according to the following rules. A susceptible patient can get the disease from an infected friend with probability 30%. A student that gets the disease will be infectious for 4 days, after which they recover. Finally, a student that is removed cannot contract the disease again nor spread it. To keep the school safe, we need to predict who will get infected in 8 days. The input to our neural network is a graph process xt corresponding to the SIR state of each student. As such, the ith component of the signal xt, which is associated with the ith student, is given by 0 for a susceptible student, 1 for an infectious student, and 2 for a student that is removed. We are only interested in tracking the infected students. Therefore, we want to predict a graph process yt, where the ith element of yt, corresponding to the ith student, is a binary label with value 1 if the student is infected and 0 otherwise. Given xt through xt plus 7, we want to predict yt plus 8 through yt plus 15. Since yt of I is a binary label for each student, this problem reduces to a binary node classification problem. In the context of node classification problems, accuracy is usually the go-to performance metric. However, in this particular problem, it is not a good choice. When trying to maximize accuracy, usually by minimizing the cross-entropy loss, one only penalizes misclassifications without distinguishing between true positives and true negatives. In epidemic tracking, it is essential to capture all the infected people. Thus, true positives are more important than true negatives, which is why we choose to maximize the F1 score. The F1 score is a harmonic mean of two other performance metrics, precision and recall. Precision measures the proportion of students that were correctly predicted as infected to all of those that were predicted infected. As we can see in the chart, this corresponds to true positives divided by predicted positives. In other words, precision is the proportion of correct positive predictions. Having a high precision means that we have little false positives. Recall measures the proportion of students that were correctly predicted as infected to all of those that are actually infected. As we can see in the chart, this corresponds to true positives divided by all actual positives. In other words, a high recall means the model is good at predicting infections, That is, it produces little false negatives. Having a high recall means that we are not missing many infections. Therefore, the loss function that we choose to minimize is 1 minus the F1 score. This maximizes the F1 score, which provides a better trade-off between false positives and false negatives than the cross-entropy loss. We present the results of epidemic tracking for a GRNN, a GNN, and an RNN, all with roughly the same number of parameters. In the GNN, the time instance, that is, the sequence dimension, become input features. As such, the number of parameters depends on the length of the process. In the RNN, the nodal components, that is, the graph dimension, become input features. As such, the number of parameters depends on the number of graph nodes. As we can see on the figure, the F1 score achieved on the test set by each architecture, averaged over 10 random realizations of the dataset, is better for the GRNN than for the GNN and the RNN. This is not surprising, as we know that the GRNN exploits both the spatial and the temporal structure of the data. Unlike the GNN, which only takes the graph dimension into account, and unlike the RNN, which only takes the time dimension into account.